This is notes for Algebra 1, Section 1.1, Operations on Real Numbers, that is formatted specifically for the Student Companion. Students, on page 1 of your Student Companion where you see Critique and Explain, underneath 1-1, Operation on Real Numbers, pause and write down your learning target. I can reason about operations on real numbers. Now that you're back, we're going to jot down some key vocabulary. Sum means to add. Product means to multiply. And quotient means to divide. We need to be remembering what those key words mean as we move into our next example. Turn the page and look at example 1. Pause and out to the side, jot down our calculator tips that we're going to need to look at here in a second. You can actually mark out example 1 as we are not going to do that example. Scroll down to example 2. Example 2 asks us to compare and order real numbers. Looking at example 2, part A, it says to order each set of cards from least, being the smallest, to greatest, being the largest number. The first thing I notice about these 3 numbers is that they are all in different formats, and that makes it hard to compare. So our main tip is we need to convert all numbers to decimal format. That will help us think of it kind of like money, like 25 cents, 24 cents, whatever, and put them in order from smallest to largest. We are going to use those calculator tips that you just wrote down to convert the square root of 1/9 and 6/25 to a decimal. Open up your calculator either on your Chromebook or by Googling a calculator app, and let's convert the square root of 1/9 to a decimal. I do square root, then I want a fraction, which was alpha y equals enter. We wrote that down, how to make a fraction. And then we are going to type 1/9. 1/9. Once you do that, press enter, and you will see what the square root of 1/9 is as a decimal. It's 0.3 repeating. Now let's do 6/25. 6/25 is a fraction. Fractions are division. So I do 6 divided by 25, and I get 0.24. I'm going to switch back into my notebook, and I'm going to write those down. The square root of 1/9 was 0.3 repeating. I'm going to put a little repeating bar and put a note. 6/25 was 0.24. Now that all 3 numbers are in decimal format, I can order them from smallest to largest. I know the smallest amount of, if I wanted to think of it like money, is 24 cents. Then 25, 0.25. Then 0.3 repeating. However, I am not fully done because I'm going to convert them back to their original format. 0.24 was originally 6/25. 0.25 was given to us in decimal form, but 0.3 repeating was the square root of 1/9. Now I can put a box around that answer because I have, as the directions asked me to, ordered them from least to greatest. Pause and try to do part B. Now that you're back, I'm going to move this image. And let's see how you converted these to a decimal. The square root of 121/25 is 2.2. The square root of 5 is 2.23. Let's see if you ordered them correctly. The smallest, I do not know what just happened. Let's just delete this. The smallest is 2.2, then 2.23, then 2.25. So double check how you ordered them from least to greatest when you converted them back. We're going to move on to example 3, and this is when we shift gears and start discussing rational versus irrational numbers. Rational numbers can be written as a fraction because it means that it is two whole numbers being divided. A number over another number. That is what a fraction is division. Some examples include 1.75. That is a rational number, and it can be written as a fraction. Let's test it out. We're going to do 1.75 and 0.001. In our calculators, there's a way you can turn decimals to a fraction if you want to double check. 1.75, I type it in, and then I use the tool Math, Enter, Enter, and it converts that to a fraction for me if it can be converted. Our other decimal to check was 0.001. I want to know, can that become a fraction? Math, Enter, Enter. Yes, they both can be. So I'm going to take that little note, and you're going to take notes with me. 1.75 was 7 over 4. 0.001 was 1 over 1,000. They both could be made into a fraction. So let's read example 3. It says, is the quotient of two rational numbers always rational? And we just reviewed quotient means to divide. So now we're going to divide them and see. If I have 5 halves, which is a rational number because it can be a fraction, it is a fraction, and I divide that by another rational fraction, will I produce a rational number? Let's find out. 5 halves divided by 1 half. We're going to use the option to make a fraction, alpha y equals enter, 5 over 2, and I want to divide by 1 half, alpha y equals enter, 1 over 2, and I press enter, I get the whole number 5. Question, is 5 a fraction? Technically it can be, yes. It's 5 divided by 1, 5 over 1. So if it, yes, can be a fraction, then yes, it is a rational number. And the answer to this question is yes. Quotients of two rational numbers are always rational. Let's check this one out. You have 5 halves, which is a fraction. It's rational. A rational fraction. Two whole numbers being divided. Over the square root of 2 over 4. We're going to add that. We do not know if this number is rational. We haven't tried an example with a square root yet. So I'm going to use what I know about rational numbers and fractions, and I'm going to use my calculator to help me decide. 5 halves plus the square root of 2 over 4. So I'm going to add 5 halves, alpha y equals enter, 5 over 2, plus the square root of 2 over 4. I have to make the fraction first, and then I can make the numerator the square root of 2 and the denominator a 4. Let me press enter. Oh, what do you notice? That's a very long decimal. Have any of our rational numbers thus far had long decimals? No. But what do we know about rational numbers? They can be made a fraction. So let's see. Math, enter, enter. Whoa, it gave me the same decimal. That means it cannot be made into a fraction. It was 2.85 and it just kept going on and on and on. And it keeps going. And it could not be made into a fraction. Well, if it's not rational, that means it is irrational. And that brings us into our next example. Irrational numbers cannot be written as a fraction. They have decimals that never end and never repeat. I kind of think of irrational, kind of like if you say someone's being irrational, they're being crazy. And irrational numbers have crazy decimals. Pause and take those notes. Irrational numbers have crazy decimals. If they're being rational, they're nice and sane. They're nice and neat. Wow, I can't spell. So an example of some irrational numbers are the square root of 2, the square root of 3, and pi. Several of our square roots are irrational, but we can always use our calculator to check. Our last example says, is the difference, if we are a difference we're subtracting, of a rational number and an irrational number always irrational? Let's find out. 5/2 minus the square root of 2 over 4. I'm going to copy this, paste it back down, change that to a subtraction. So we're doing the same two fractions, but now we're changing that operation. Let's test it out. If you're subtracting an irrational number, do you still get irrational? Yes, you do. Look at that crazy long decimal. That's irrational. But we can always try to make it a fraction, math, enter, to double check as like a last way to check. But I see that crazy long decimal, and I'm thinking, you are a crazy long decimal. It was like 2.14 something. It cannot be made into a fraction. That means it is irrational. I'd like you to pause and try the other two operations for me. The square root of 3 times the square root of 2, and the square root of 3 times the square root of 3. And then make a decision. Is it rational or irrational? All right, the square root of 3 times the square root of 2 was a 2-point-something long decimal. It could not be made into a fraction. It is irrational. So if you multiply those two irrationals, you get an irrational. What about the last one where the square roots are the same? Did you get 3? Well, 3 is a pretty nice, neat whole number. It doesn't have any crazy long decimal. 3 is rational. So pay attention to the multiplication of two irrationals. They're not necessarily always going to lead you to a rational or irrational like other things are. Rewind and watch as you need. This was 1.1.